So welcome everybody, thank you for coming to the talk on deep learning for mobile. So just before we start, a little bit about me. I'm Jan van der Poel. I co-founded a company called Flowpilots that makes enterprise mobile applications mainly in Belgium. So we started in 2011 and we did web applications, PhoneGap, then we went to Java and Objective-C, hit the wall on all three platforms, and then Xamarin came along and we started to do a lot of Xamarin applications. Since about a year, I've been doing a deep dive, no pun intended, on deep learning to become an expert in that field. I write about my studies on a small blog called Zero to Singularity, starting from zero and going to the singularity, which is kind of a joke. Most people in the AI will probably get. And then apart from that, I love to do some reading, and I'm starting to run again. I'm trying. All right. So the goal today is a little bit to teach you what deep learning is and what it can do. There's a lot of hype in the media, and I hope that that will go away. There's a lot of cool stuff coming out, but it's hard to reproduce. So I wanted to show you, okay, what is deep learning and what you can actually do with it. So take away a little bit of the magic. It's basically really simple math, but a lot of it. But I won't spoil any of it. And give you the basics to get started. So with a focus on how do you do the deep learning stuff on a mobile phone using Xamarin. First, some definitions. People use AI, ML, so machine learning and deep learning, a little bit of interchangeably, and I don't think that's okay. This is a little bit how I see it, is that artificial intelligence is basically any computer system that tries to mimic human behavior. The stuff that I was coding up in the early 2000s, that had nothing to do with machine learning. We were doing depth first, breadth first. So it's trying to search without implicitly being told where to search. Now, a subpart of AI is machine learning. So using statistical methods to try to get some information, to learn something from data and not being explicitly programmed. Now, it's mainly statistical models and what we call shallow networks. Now, deep learning is, as I see it, a little bit what all the fuss is about these days, and it's mainly that we have large, very, very large networks, and I'll come back to the network part. So very large strings of mathematical operations that produce wonderful results. Now, in traditional programming, basically, if we're writing a mobile application, say for a bank, we as imperative programmers, we tell the machine what to do. We say, I want to log in, so make sure the fingerprint of the face is detected. If that's okay, then fetch all my accounts, show all my accounts. If I click on a detail, show me all the transactions that I did. I tell the computer as a programmer what to do. In machine learning and deep learning, we try to get to some functionality without explicitly programming it. So we start with data, labeled data, unlabeled data, and then we try to teach the system something and then get to the result. So basically, the computer learns to do a particular task and learns from experience, not without being explicitly told. So what is deep learning? And I'll give you some examples of what we see in the media. So this is AlphaGo from DeepMind. Up until that time, Deep Blue was the chess computer from IBM that beat the world champion at chess. But it's not really intelligent, it was just sheer power that calculated all the paths possible, then which next move has the highest probability of winning, and then played the game. In the game of Go, I'm not going to dive into all the details, but the board is 19 on 19, and every player just puts a white and then a black and then a white. So the number of options are too much for a computer to calculate the entire possibility tree and calculate the possibilities. So it had to learn and see and play and teach itself by playing against itself and improve by doing it a lot, and then play a human. This is from Google Translate. So Google Translate, when it was released a number of years ago, it had really laughable results, but it's getting better and better. And nowadays, if you're using Chrome, you get a small button, you click translate this page, and it's usually quite correct. I translated this from Dutch to German, and now my German is good enough to detect that this is not correctly translated, but it basically says my German is not good enough, so I'll be presenting in English. I think I can fix the errors, but this is not explicitly programmed. If I write this sentence, then this is learned from experience, from looking at a lot of Dutch text and a lot of German, English, Korean, whatever text, and then learning what should follow after a given word, and then create the translation. When we look a little bit at images, there's a gigantic data set called ImageNet. Basically, it's a lot of images of cars, dogs, people, and they have labels. So the image of a cat has labeled cat, image of a dog has labeled dog. Yeah. For a number of years, people have been trying to be able to predict unseen images, what label the image should get. If I see an image, if the computer sees an image, is it a cat, is it a dog? And for humans, this is very, very easy. We know what cats are, we know what dogs are, we see the image, and we say, okay, definitely a cat. For computers, this is hard. Now, up until 2011, people were using this quote-unquote historical techniques to detect or to instrument the computer as how to detect whether it was a cat or a dog. Now, from 2011, Alex Krzyzewski, I hope I say his name right, from University of Toronto, used a method called a deep neural network to try to predict the results, and the performance was 10% better than the previous year. And from then on, all the new entries every year, it's always better and deeper neural networks. If we look at the human performance, humans make about 5% of errors by looking at those images. Sometimes it's very hard to see whether it's a cupcake or a dog. But computers have the ability from 2015 and 16 to do better than humans. So they beat humans at looking at things and recognizing things. Now the trend that we see, this picture is reversed. Sorry about that. So the years go down if you go to the right. You see that they started at shallow networks, just a few layers. And then as time progressed, more and more layers were added. And I'll explain why that was possible at the time later on. Now, if you look at computer vision, there's a number of tasks we can do, and computer vision scientists are saying, okay, but how much does the computer really learn about what is in the image? And the first task that you can do is classification. You see an image and you say, okay, this is a cat, this is a dog, this is French fries, whatever. Next part is saying, okay, I know this is a cat, and I'll show you the bounding box of the cat. A little bit harder. The next one is object detection. For all the classes that the computer system is trained on, it is able to say, okay, picture I have never seen. In this picture, there's 2 cats, 1 dog, and 1 duck. And by the way, these are all the bounding boxes. The next part, the final one, is segmentation of the scene. So if the computer is able to meticulously detect where the cat is in the picture, and you'll be able to swap out the cat for another cat, for instance. Now the computer vision says, okay, is that smart enough? So we go a step further. We teach the computer to say, okay, here is an image. Describe in a sentence what is in that image. So on the right, on the left, there's a number of good ones. So it's a person riding a motorcycle on a dirt road. That's a pretty good description. The other ones, it's a little bit difficult, more difficult, but you see the computers get smarter and smarter, and they are able to do a lot more sophisticated tasks. Then they say, okay, it's easy to just capture an image and train a lot of images and generate stuff. We want to be able to answer questions. So have the computer answer questions. What is the vegetable on the plate? Well, it says broccoli. How many buses if I were to look at the image and say there's one bus, well, there's actually two, because there's one bus hidden behind the other one. So the neural net was able to say, okay, I see two buses, and it's able to interpret the question and answer it possibly even better than humans. Now, there's a lot going on about explainability. Why do we take these decisions? Here, there's a paper on, okay, there's a woman throwing frisbee in the park, and by the way, the frisbee, I think this here is why I say it's the frisbee. There's a stop sign on the road. Well, I think there's a stop sign, and then it highlights the stop sign. And I'll show you later on how that works and how they detect those things. This is an example that you see a lot in all the media. It's because it's visually cool. AI is able to understand, okay, this is an input picture, so on the left, and then in the middle, there's a style of a painter or a scene or whatever, and it's able to translate the input image because it understands this is the context of the scene, and this is the context of the style, and merge those two together. An image-to-image translation, you have a painting of Monet, and AI is able to realistically generate an image of that landscape. So content generation based on images it has seen. And then this is a cool example of generating content. So based on training data, we're able to generate a zebra from a horse. This is a neural Photoshop. So basically, instead of manually doing everything yourself, AI is able to, okay, these lips, I know where the lips are, and I'll update the color. If I do the hair, then I know not to just change here, but if on the right side of the face there's more hair, then the rest of the face should also be covered more. Now, final example, this is pretty recent from OpenAI. Okay, this is an input image. I want the image to smile a little bit more. I want the image to be a little bit older, a little bit younger. And this renders in your browser. So that's pretty fast. Oh. Another one more from OpenAI. This was in the media recently on Dota. Does everybody know Dota? So it's a multiplayer massive online game where an AI was able to play against humans. So they have to be able to control the figures and collaborate on a strategy. Now, at the moment, the humans are still ahead, but it's a matter of time and training before that will change. Right. So why is this happening now? I was doing, before we were discussing, there's people in the audience that wrote a book on neural networks in the 90s. I was doing neural networks in the beginning of 2000s, and my professor was telling me, don't focus on neural networks, support vector machines, which is a machine learning technique, that's the future. Because you have very little parameters that you have to tweak, and it works amazing. There wasn't even talk about deep learning yet. It was neural networks, and there's too much parameters that you have to tweak. It's impossible to compute. So why is this happening now? Well, there's 4 reasons. First of all, there's a massive amount of data. Amount of data that we generate, pictures, data online, annotated. So Instagram is basically all annotated pictures because we put hashtags on whatever is in the picture. So there's a massive amount of data, and this is required. Why? The more data we have, the more performant, the more performant the system can become. Secondly, it's GPU power, sheer computing power. So I put an image of an NVIDIA graphics card. Why? Because at the moment, NVIDIA is the dominant player in the market. If you want to train a network, 99% of the time you have to do it on NVIDIA. Intel is getting into the game. They recently acquired a company called Vertex that had a project called, I don't know if it's Plate or Plate ML, where you can train your network in Keras TensorFlow on any hardware, so any GPU. Improvement in algorithms. So I mentioned that deep neural networks are basically a lot of mathematical computations multiplying numbers. Now, if you multiply a lot by a small number, or multiply a lot by a large number, at a given moment in time, you will not be able to reproduce the smallness or the greatness of the number. So you have underflow and overflow. Now there's techniques on how to solve that. So yeah, improving the algorithms that are used to make it possible to have these long strings of mathematical computations. And fourth, and this is often forgotten, but in my opinion, the frameworks are very important. Back in the day, which means 15, 20 years ago, you had to program everything from scratch. And now, frameworks allow you to write a number of steps in Python, and you're good to go. Basically, where you spend your time is data cleaning and data cleaning. The algorithm, it might train a few hours, but who cares if you spend months on collecting and cleaning your data. There's some myths about AI. A lot of people think that you need a PhD. I'm here to tell you that you don't. You don't have to take my word for it. I'll come back to this later, but it's the same as using a database engine. If you use SQL or Link, you don't have to know everything that's beneath it. Deep learning is now in a high stage where normal media are reporting on research results. But there's a lot of steps in between where you can use what is out there without having to come up with the next fantastic algorithm. Obviously, there is room for PhDs in deep learning to do fundamental research, but it all depends on what you want to do and where you want to be productive. So you need big data. This is partly true, but if you do a specific application, you can reuse a lot of what somebody else has done. This is called transfer learning. So you use a trained model, and then you retrain it with a number of your images and just change the end. And then you're good to go. So if you have 20, 30, 40 images per label, we'll train one with 10 images per category. Later on, you're good to go. So you don't need billions of amounts of data like the Googles and the Facebooks of this world. But not necessary. Expensive GPUs, I'll pick out some of them. Expensive GPUs, if you have one or two moderate GPUs, that's fine. If, as I said, you'll be collecting and cleaning your data a lot more than you'll be running your GPU. I say use two if you're really doing stuff. You have one to do like training a specific model and one to do your experimentation, and that's it. They cost 700 euros a pop, so you don't need. There's papers coming out saying, hey, we did this fantastic technique on using 20,000 GPUs or 2,000 GPUs. I don't have the budget for that, but yet I do deep learning and apply it. So I mentioned that we learn from experience, and I'll discuss a number of ways that we can train computers. So there's three main types of learning. The first on top is the supervised learning. Basically, you have like ImageNet, you have pictures and labels. So we have the input and we have the expected output. If you see this image, this is a cat. If you see this image, this is a dog. We can train and we can try to predict, see what's wrong, and improve and gradually get better at the job. The other one in the bottom left corner is unsupervised learning. Basically, you have data and you're trying to get information or hidden structures within that data. So you don't have a final result, you're trying to look for something that is in the data which is not obvious. You can use that to generate new data. So you have a lot of images, generate new data, generate scenes, generate images. That's unsupervised learning. And finally, it's reinforcement learning. Reinforcement learning is where an agent moves around in the world with a certain objective. And it performs an action, and it gets a reward or a penalty. And by doing that a lot of times, it learns how to interact within a given system. So a lot of the OpenAI on gaming research is using reinforcement learning. Now there's one more, I mentioned it previously, it's transfer learning. And this is an important one if you're going to be applying deep learning yourself. You use what is already available, and there's a lot of material available, and you just tweak it for your own needs. This will save you compute time, this will save you time in collecting your data, and this will make you a lot more efficient. And from where I stand, that is what I try to focus on. So now, going into the deep learning for mobile, there's a number of things that we have to consider. Do we do it on the device and off the device, or off the device? So in the cloud. This goes for inference and training. What is inference? Inference is basically just production. So in training, we show it images and then we get feedback and we improve. Inferences, we show it feedback and then it says, okay, I think this is a cat 60%, 80%, 90%. That's inference. It's production. It's same way. Okay? And then basically, is AI as a service or do you roll your own? These are the choices that we have to make. Now for the demo, we'll be building a small app, Xamarin app, which will be able to classify cats and dogs. So very good performance of 90%. And we'll make different versions. We'll use the AI as a service and we'll use the API. And then we'll use the AI as a service in the offline model. So basically just on the device. Thirdly, we'll run our own offline model. So we'll do everything, quote unquote, from scratch. Build the model, train the model, convert the model, deploy it, and use it in our application. Now, why would you want to do the first thing? So the first thing is we use an existing AI as a service. Basically, we're mobile developers and we want to get things done. We want to have a classifier. There's probably might be no time, no budget, no expertise to do it all ourselves. But we want to be effective in our job. How do you do that? There's a lot of these offerings. We'll be using the custom vision from Microsoft, but Google, Amazon, they have similar offerings, which I did not list all the capabilities because they basically change on a daily basis. There was a lot of news on Baidu releasing EasyDL, so easy deep learning, but it's unavailable in Europe for some reason. So you can use it in Switzerland, maybe everywhere in the world except for Europe. I don't know why. So I can't report on that. What we'll do is we'll train the model and then we'll consume the model first via an API and then via an offline model. So how does that look? First step is we collect images, and luckily we have a data set. So you collect images on what you want to classify, and you label them. So think about labeling 10,000 images by hand. I had a customer I was talking to, and they had a specific problem. They wanted to detect something, so the location of an object, and say, okay, how do we solve this? We've been looking at this for a week, and we are unable to crack it. So the algorithm is there. This is the link. This is how you apply it. The only thing you have to do is for every class object that you want to detect, you have to generate about 30 to 40 images and give it the bounding box. So that's how much we want to do it. Yet they spent a week on figuring out how to do it. So we'll collect the data and make sure we can use it for training. Then the second step is we'll use it in an API. Basically, we have a mobile application. We take a picture of a cat. We send that picture to the API where the model is deployed, and it gives us back a prediction of, I think this is a cat with a problem. Thirdly, we'll just do it on the device. Okay. Now I'll switch to demo mode if I can. Bear with me. So for the demo, as I mentioned, we're using custom vision from Microsoft. You can start playing around with it for free, and then after a given time, you have to pay a small fee for the storage and the number of requests you do. So I created a project. Now, if you create a project, there's a number of options. Obviously, a name, but these are the interesting ones. So, do you want to do classification or do you want to do object detection? You see that the object detection is in preview, meaning that if you want to do stuff like
the image segmentation, you can do it in the AI as a service yet. So that is why I mentioned, depending on what capabilities are available, you might have to roll your own anyhow. If you select classification, then we can do multi-label or multi-class. Multi-class meaning you send in an image and you get a result back. This is a cat, this is a dog. Multi-label meaning this image contains cat, dog, a number of domains. So there's 5 domains and then compact. We'll use, if you do mobile, use the compact. Why? It's, as I mentioned, deep learning network, there's a lot of mathematical computations. There's no powerful GPU on the mobile device. So there are slimmed down versions to work on mobile that give you good performance if you want to do it offline. Okay, so I already created the cats and dogs project. The next step is uploading images. I took these from a Kaggle competition, so I did not invest a lot of time in making and labeling these pictures. You just basically upload them and then add tags saying, okay, these are cats and these are dogs. Simple as that. Next, we click train. Obviously, nothing has changed since the last model. I'll add some images. I'll add some dogs. So I'll tag these as dog. Okay. Next, I'll train a model. So what it's doing now is in the background, see later how it works, but in the background, it is training for me and it's already done. So big GPUs, lots of data. I think we have about 40, 50 images and it took under a minute, 2 minutes to get some pretty decent results. Next, we can, hold on, I'll do the quick test first. So we can start testing our model to see if it actually performs. What you do is we send in an image that it hasn't seen before. And it tells me that 100% sure that this is a dog. This is all under 5 minutes that we've been training and working with it. So I'll show another, I'll try a cat. Not sure what will happen with this one. So this one says it's a dog and that's wrong. Yeah? So obviously it's not perfect. What you do is, in this case, you look at why it's, one, it's kind of a hard picture, two, you probably need more data than 20, 30 images to get it right. Next thing I did was I'll use the prediction URL to create a curl script, small, just to test the API and see that everything works. While I was creating the demo, so the custom vision is deployed in central US. They had a lightning strike and nothing was working. So one day the API worked, and the next day I was getting errors in my app, and it said file not found. And I spent half a day looking at this, and then I contacted somebody at Microsoft. Yeah, we're having a little bit of an issue. The thing is down. Why am I getting it? Apparently there's an error that you get. Just nothing to do with anything, but it's the first error that you get, so you start looking at it. I get
the real cloud hits the version.
yeah. Okay, so you can simply create a curl request. I need my notes. Should have had those open, I'm sorry about that. Hold on. Now all my thoughts are being recorded. Not sure what it's okay. You don't need to read it. Nice. And then, so I created a curl script. Basically, what it does is, can you read that? No, that's what I thought. Hold on. Jump it down. So Okay. So the curl script is basically the endpoint with my project number, the prediction key. Say I'm using the binary string, and then I point to the image on my local disk. If we hit enter, this should return. Did I change something? The previous one worked. Okay, just took a little bit longer. Yeah, so it returns some JSON, as everybody does. You use JSON beautifier, paste that in, and then we see that, okay, for this project, it predicts 100% that it's a dog and 0%, so you get a JSON back. Now, how do we use that in a mobile application? So the mobile application we're using is based on the template that you generate if you click New Forms application. It contains a shared core and then an Android and an iOS application. Nothing fancy. It has one view that is particularly important. It's the detail page. Detail page. Where all the magic happens. I'll start on my phone. Do I share my phone as well?
If you can.
That's quick.
Quick time there.
And then new recording session. Here's my phone. Is this working?
No. It's a little bit buggy. This is full screen.
Yeah, but it only works on my phone.
It's buggy.
Something is crashing. I think it's QuickTime. Okay. Hold on. I'll show you the app on the simulator and then the results on my phone while I try to get the QuickTime up again. So don't tell my girlfriend that I can do 2 things at once. She won't believe you. All right. So this is the application. Yes. Thank you. We have 3 items. So we use the custom vision API, we use the custom vision offline model, and then we use the custom trained model that will build later on. So first, we use the custom API. If I click here, I will need to make an image that gets sent. So I'll try to get QuickTime once more. This should work. I have to do it on my phone.
You have to wait some time.
Yeah?
Yeah. It takes a while.
I'll just run it on my phone and then they should be done at the same time, right? That's how that works. Installing, I hope QuickTime joins us. I'm missing a QuickTime screen, no? Okay. Sorry for the people on the live recording. I'll go to the data gaggle and we'll take a picture of a dog it hasn't seen before. Yeah. We'll check out the code after this. Okay. So it's identifying and it tells me this one is predicting 97% that it's a cat, which it is not. So we need to improve the model. Try one more. something that looks like a dog. So beating human performance. Right? So 100% that it's a dog. So basically use more than 20 images for this. Right. Now how does that look? To be honest, it's fairly easy, but there are, as always, some caveats.
Can you upscale the font size, please? Yeah, thanks.
Yeah. This one?
Yeah.
I think I can, yeah, I can zoom in as well. That's not, okay. What you do in the dependencies for custom vision is that you add a number of new units. You add the cognitive custom vision prediction, Microsoft REST client runtime. The media plugin is just for easily taking pictures. And then I use the on-device custom vision from Jim Bennett, who will be at the expert day. He wrote a blog about this as well, and the plugin that you can just drag and drop and use in your app, which is always nice. So thank you for that, Jim. What you do is first you create an endpoint because we're going to talk to an API, and we add a prediction key. So looking at, you just look at the settings, and then we'll need the project and the prediction key. Yeah. These are basically API keys. See, there's less and less magic in the deep learning part, right? Use the prediction key, and then you add these 4 lines of code. So I check whether it's custom vision, and then we predict an image using the project ID and the stream of an image. We wait for it to return. We get a list of predictions. We order them by probability, and then we return an update RUI. So talking about being productive, this is it. Unless the API is down. If you, no, seriously, but if you debug this, you will, once you do the predict image async method, you will get a file not found error, and then you have to wait a while. So I think it needs to spin up. While you are waiting, you think it's the file not found, that it's an error. It's not. I'm not sure. I'll try to find out what it is, but it's not an error. Don't spend a day like me on it trying to find out what permission you forgot to set in your iOS application to use picture. It is not an error. You get a bug, you get an error for it, but it won't affect the runtime. So I have to check why. But just step over it and wait for the API to return. Now sometimes in mobile, I used to say, or I still say, that everything needs to work offline. If you open an application, although there's 3G and Wi-Fi, even if I'm in Germany here, I do free roaming now with the new regulation, but it has to work offline. If you're in the basement, if you're somewhere, it has to have a default setting. For deep learning, you can run the model offline. How do you do that? Using custom vision is that you select, so one of the trainings you did, and then basically click export. You select the platform you want to run it on, and it will export the model for you. I'll show you later how you can do that yourself, but for now, this is fairly easy, right? You just click, you get the model, wait a little while. Did I click it? Yes, I think I did. Okay. And then you download it. It's 2.8 megabytes, but that's also why we use the compact model. If you use regular models that are very, very large, they can go to a couple of hundreds of megabytes, which you just don't want in your app. They give good performance, but probably not on the GPU of your device. Okay, we'll have a look. So this is an ML model. Should it name that? There's one step you have to do in between, and then it's converted. So you have to not convert but compile a model. In the documentation, they state that you can just mark it as a core ML model and then it will compile it for you. That didn't work for me. So you have to run, if you run core ML compiler, file, and then it's not ML, and then that should work. Right, and we're done. This creates a folder which is as the ML model C, which is the compiled model, and this we import into our application. So basically, the iOS parts, under the resources, we do add from existing folder. I go to the downloads, there's cats and dogs, and I just add all the files in.
What was the preferred export file, the ML model for iOS and the TensorFlow model for Android?
Yeah, so bear with me. On iOS, you use Core ML, and Core ML requires a compiled ML model. On Android, you use TensorFlow PB file, so protocol buffer. So if you, for instance, if you probably use Keras to create your model, it will save that in an H5 file. You can convert those. So there's a number of tools to convert from Keras to Core ML, from the Keras to the PP file. So I'll show that in the next part.
What's inside the model? Just the neural network weights
and the model architecture.
And the architecture.
Yeah.
How many layers and
yeah. So which layers, and if you're using dropout, not dropout, because that's a training.
You saw the folder names.
Yeah.
When you were testing.
Well, bear with me. I'll finish this part and then we go to the.
Okay.
Right. Okay. To do this, so the offline part using custom vision and Jim's plugin is that you add the plugin and then you create in the app delegate you say I want to use the cross image classifier and my model is called cats and dogs to initialize, and then in your shared code.
And for this I need this NuGet package or?
Yes, yeah. So for the previous part, you didn't need the plugin for the on-device. That is only for when you use the offline model. Okay. So again, if you use the API, you just need the cognitive custom vision prediction NuGet. If you do on-device predictions, then use the on-device custom vision from Jim. That gives you the cross image classifier. Yeah.
But it's just for image classification or for other model types?
So now this one supports the ones, this is specifically for Core ML. So it talks to the Core custom vision backend.
Okay.
I think he recently released a NuGet for text and speech. But I haven't looked into that, but I can give you the link if you want. So the NuGet from Jim is really using custom vision from Microsoft. He is developer advocate for Microsoft, so it kind of makes sense.
Yeah.
Okay, so in the detail model, here. So this part is basically, again, we get the file, we say classify the image using the stream, and then we'll return a set of tags. We select the one with the highest probability, and we're done. I'm not going to run it because you can't see it on the phone, but it basically is just, it doesn't send the picture to the backend, it uses the local Core ML model to make a prediction and give you the results. Okay. Now, sometimes you need more control and you need to roll your own. For instance, if the AI application as a service doesn't provide what you want. So at the moment it's classification and preview on object detection. If you want to do other stuff, those scenarios are not supported. Maybe you don't want to put it into, for legal reasons or financial reasons, put it in their cloud, but you have your own proper setup that you want to use. You can do all of this yourself without getting a PhD. Now, before we go to the demo, we'll dive a little bit deeper into what it all means. I won't go as far as to do everything, but I'll give you an intuition as to what it is. So, neural networks are modeled after the brain. I won't go into all the details, but the idea is that you get some inputs, small computation, and then you send out a signal or you don't send out a signal. Yeah? So that's how our brain works. A lot of these neurons are connected and they send electrical signals to each other and then they fire or they don't fire. If we do that mathematically, on the left side we have a number of inputs, set of inputs. So if you have an image, every pixel of your image is one of these inputs. So an x1 is one pixel, x2 is another, and another. So we stringify the image and we send it through. We do a small mathematical computation as to x1 times w1 plus x2 times w2. Yeah? We add those up. That's the linear part. The second part is a nonlinear part, which is an activation function, which is nonlinear. I'll show you an example. So the input, it transforms it into something nonlinear. Now, combining the linear and the nonlinear part, we're able to approximate practically any kind of function we want using this basic model. Yeah. Now, what if so the input layer is the image, the output layer is whether the network says, hey, this is a cat, this is a dog. And in between, we do a number of computations. Now, instead of doing a few of these, deep learning basically means we're going to do a lot of these. That is why it's deep learning. Now, there's a number of different architectures. I put this in for reference as to how you connect these dots with each other. As mentioned, we call them deep networks because on top you see the ResNet that won in 2015, which has a lot of these mathematical computations. I'll explain the most important one for vision, and you'll see it's basically very simple, but it's kind of genius. Now, how does that work? And it's called the convolutional operation, called convolutions. On top, you'll see something called a kernel. It's basically a set of numbers that we'll use in a minute. On the bottom, you see a blurred object of a face. And then a red 3x3 square. Now, everything it does is we move the square over the image, pixel by pixel. And at every point, we do a small multiplication. So where we are, we see that the pixel value, top left, is 49, and we multiply it by -1. Next to that is 74, we multiply it by -1, and so on and so forth. Yeah? We sum those up, and that value is the result of that pixel in the next image. Now what happens is, you see that we reduce the image to its basic structure. Now, if we do that a lot of times, and I'll show you some images later on, then the network will be able to see and learn to see and combine things as to how to construct and what is a human eye, what is a beach buggy, what is a dog, what is a cat. Is that, I see a lot of, is that clear? Or? Okay. Now, how did they learn? Basically, in the first layer, they learn like small shapes. Diagonal, straight line, nothing special. Now, as we progress, they start to combine those things, And we see parts of a sunset, parts of a field, and even further layers, we start to see like the wheels of a car. And in the end, it gets combined into humans, into dogs. Yeah? So it learns basic structures and starts combining them into real-world objects. Now, if you want to train a neural network, we need three things: data, a network architecture, and a loss function. How does that work? On the left, so training is on top. On the left, we have a lot of data. The dots are our architecture, and in the forward pass, we pass all our images through that network. Well, the network says, okay, this image, I think it's a dog. This image, I think it's a cat. And then we'll compare those with the actual labels. So I think it's a dog. Is it actually a dog? In the backward loop, we say, okay, we have an error of, at the moment, 80%. So that's really bad. We need to update the weights a little bit. So we need to update the numbers in those neurons a little bit. And then we try it again. That's basically training of a neural network. Yeah? So we shove the images through, we make predictions for everything. We calculate how close are these predictions. We update everything a little bit, and we try it again. At inference time, so in production, we just do the forward pass and say, okay, this image, I think it's a human face, I think it's a dog, I think it's a cat. Yeah. So now for the demo part. First, we do the training. Training, again, we need the images that are labeled, but we can do that whatever we want. We can do that on a server, you can do that on your laptop, you can do that on a desktop machine that you have under your desk with a lot of GPUs. And then inference time, you can deploy the model in an API. I'm not going to demo that, but in the bottom, we're going to see how we can convert the trained model to something that we can use on the device, so iOS Core ML, and then see how we can use that. It's a little bit more work, but you get a lot more control. I'm not SSHing into Azure, I just nickname it like that. So what we do first is we need data. So in order to get the data, I wrote a small library called PDL, which is the Python download library, where you have a lot of, you can just reference the URL, it downloads and extracts, or you can have a lot of helper methods for the most popular data sets. So the dogs, cats from Kaggle, you just do dogs, cats, it downloads it, extracts it, and you're ready to go. Obviously, I already ran that, and in the data folder, we have the dogs, cats dataset. Now, the second part is how do we train the model? Can you guys read that? Or do I need to zoom in? Yeah? That one? Better? Okay. So this is taken from the Keras blog, which is create a simple network and train it on your own data. I'm not going to step into every detail of how Keras works. I'll give you some of the details. So we specify the image sizes, where the training and the validation data is. So basically, we train the network with images, and then we use validation data to see how good it is on data it has not seen before. Yeah? So at training time, you need 2 sets of data. Custom Vision takes care of this for you. You have to do this yourself if you want to train the network. What does that mean? You create training images to train the network, and then test it with images that it hasn't seen before. Why? Because otherwise there's a possibility that it would just focus too much on the images that it saw and would be unable to recognize images from a dog that it has never seen. So we specify the number of training samples, validation samples. We'll train for one epoch. So an epoch is basically we run through the entire data set once. Normally you would specify a larger number, but for demo purpose we just do it once. And then the batch size is basically, well, from the 23,000 pictures, we'll jam in 16 images at a time before we update again. Okay. Now, creating one of these models that we saw is fairly simple. You say it's a sequential model because the layers are stacked right after each other. And then you start adding convolutions. So it's basically all blocks of this. Now, this is why I say that the frameworks take away a lot of the hard things. This is the only thing that we have to program. So we have to say, do a convolutional operation, nothing of the fancy math that I explained, nothing of updating the weights, the framework will take care of that. So if people start talking about partial differentiations, it's true, but you don't need to know that, because all frameworks take care of that for you.
Actually, in Keras you can even download all networks,
yeah,
which have been
so that's
for you.
That's
even easier.
Yeah, so that's the second step. So this is where we train from scratch. So we create an architecture, we initialize the weights at random, and then we train. This will, for a lot of images, will take a lot of time. As I mentioned, there's a technique called transfer learning. You download a set of weights, so a network architecture and weights, and you retrain them on your own images.
And you can also download them without the weights.
Yeah.
So.
But you can define the layer structure with this script?
Yeah.
Okay.
So basically you just write that out. Now the thing is, it's not that easy to write a good architecture. So there's a lot of people doing research and building models, and every year they try to get better at ImageNet. But it's always very specific architectures, very tweaked, a lot of work into giving them the right structure, because switching it around a little bit might give you very different results. So what I suggest as a user and a practitioner is download pre-trained networks and weights that you know will work and retrain them on your own images. If you want to dive deeper and say, I want to create a new method or do research, then you do this. But 9 times out of 10, you say, okay, give me the weights, give me the architecture, and here are my images, and retrain. It's going to be a lot more precise and a lot less training time. You'll get better results. It's in one of the references, but I think it's good to tell now, is that there is a course Fast.ai, Fast.ai, that have a lot of videos. I think it's 16 videos on teaching everything you need to know about deep learning without overloading you with mathematical things. And in the first lesson, they train you to build an image classifier that is 99% accurate or 98% accurate in 4 lines of Python. And what they do is they build it on top of an existing architecture. They download the weights, but that all happens in the background. You just supply the images. They use a number of really cool techniques to get up to improve performance. But with 10,000 images for this one, they get up to 98–99%, and it takes, I think, on a regular GPU, a couple of minutes to train. So 4 lines of Python, 3 minutes of training, and you blow away all the ImageNet results prior to 2016. So that mind, well, it's in the references, so be sure to have a look if you're interested. There's some really cool stuff in there. So this is really...
And the models are free to download? Or?
Yes. So the architecture are known. You can even if you do model.summary. Hold on. I think it's no. This is model info. Yeah. Basically, if you do this line model.summary and you print it, you see the entire architecture of the model.
Oh.
And if you initialize the model from them, you can. But excuse me, the models are no secret. So what the architecture is, it's not a secret. There's a number of, for every model, pre-trained weights that give you very good accuracy, and you just pre-train them on your own images. The question is, and I'm not a lawyer, but how legal is it to, for instance, ImageNet? ImageNet, if you want to download ImageNet, you have to certify that you will not use it for commercial use, that you are a researcher and that it's only for non-commercial.
Yeah.
But you don't actually, in the model, you don't use the images.
No.
You use weights that are trained on those images.
Sure.
Now, I am absolutely not a lawyer, so I can't tell whether that is you should or shouldn't use. I think I would use it.
No one can prove it.
Sorry?
So I think no one can prove that you use these images from the source.
So there is no prior, as far as I know, no prior work on that, or it never happened that a large company said they were going to sue you because, or ImageNet said they were going to sue you because you used those commercially. I tried to, just before I was Googling it, I don't know why, and I tried to look up whether there was a commercial license for ImageNet, but I couldn't find it. And then there's a Reddit, I think it's a Reddit post on a discussion on whether or not it's legal or illegal, but that's stuff for lawyers. Because it's a derivation of those images. Honestly, I couldn't tell. But, to come to your question, the architecture is usually open, weights, you can easily get them, and then just retrain on your images. So what we see here is basically a very simple model, some convolutions, some activations, and then in the end we say, okay, we use a sigmoid activation to classify whether it's a cat or a dog. For some reason, I'm back. Okay. The SSH connection is not that good, but I'll do my best. Basically, we compile the model, we specify a loss function to evaluate how good we are doing at a time. We use an optimizer and metrics, but at the moment that's not important. An optimizer is how we update the weights. It's usually very simple mathematics, but you have to just use it. We generate data, and this is data augmentation. So what that means is say we have a set of 10, 100 images. Using this technique of data augmentation, we give the network small variants of that image. Yeah, so we flip it around, we turn it a little bit. So to us, it's still the same, but the computer gets an entirely different image. So basically, we multiply the number of possible images that we have and showing it to the network. This again, you don't have to program. I'm trying to scroll down, but it's not working. So you don't have to program this. This is all in the framework. Yeah, and then we fit. So then it will start training and updating the weights. And then later on, we save. There's a number of ways you can save. I saved it in 3 ways because the model file is easier for CoreML to convert. The H5 file is easier for Android to create a protocol buffer. Yeah.
Can I write this only in Python, or is it also available as API for C#?
There is a binding for TensorFlow in C#, but you can't do back propagation, so you can't do real training. So therefore, I would advise not to use it. Also, Everything else is in Python. So all the helpers for getting the model, getting the weights, it's all Python. So this PyTorch, Torch from Facebook used to be in Lua, but they just created a Python API. I think in data science, if I'm wrong, but Python is the glue for everything you do within data science. There's a Python library that connects to. And this is not a case for beginners. This is pure practical. You can do it in any language, but in Python there's so much available.
So it's a little Python, more or less.
Yeah. I mean, how long can that take? It's a scripting language.
Yeah.
Okay. So next step is we run that script, we train this. So yeah. So if you do this a number of times, or for multiple epochs, so multiple times that you see the entire dataset, this can take a while. As I said before, that's okay. Get 2 GPUs, one can train, one you do experiments, or you code your application. I mean, the data part is, hey, I grabbed this Kaggle dataset. In real life, that's where you spend the most of your time. There's data scientists in the audience, check with them. Usually data scientists don't build fancy deep learning models, they clean data. The infrastructure is a big part. Once the company has infrastructure for data that is accessible, that is clean, that is ready, then you can do training. And then if you, as I said before, if you spend months on cleaning your data, whether your model trains for an extra hour, nobody cares. You're gonna need the extra hour to get over the data cleaning for 7 months. What I found, and I need to look into why that is. It's possible, maybe not hard, but I don't know it. Is that for the Keras model, it takes me a really long time to train. If I do say 50 epochs, it would take me 2 hours. If I use the same graphics card when using FastAI, which is built on PyTorch, it takes me a couple of minutes, and I don't know why. There's got to be a reason. It's not bad engineering, it's just something different. But at the moment I don't know why. Yeah, so this one it used to take about 163 seconds. I ran this a couple of times, so I know. I'm gonna kill it because we have obviously those outputs here. Don't know why the SSH connection is so bad. Okay. So we store that in a .model file. Yeah. So in Keras you just say save model to ML, and then we do a conversion from Keras to Core ML. What happens is you set the class labels. So we have cat and dog. We load the model, and then we use Core ML tools, the Keras converter, and you're good to go. So the input name, output name, scaling, and setting the class labels, and then it's converted. It's fairly easy, but you just have to know it. There's on the frameworks page, I didn't mention, but Onyx, ONNX, is a standard from Facebook, Amazon, and Microsoft, where they try to become the interchange framework for neural networks. So they have an architecture or a standard and the tools to convert from one framework to another. That is work in progress. One player, Google, is not playing along, but as you can see, there are Core ML tools from Apple where you can just use the Keras to Core ML, so you don't need the Onyx. For PyTorch, you need to go through Onyx and then to Core ML, which can be a little bit of a hassle. I started the demo in FastAI and in PyTorch, to be honest. I still need to work on that. So once it's converted, you save it to an ML model, and then the ML model we can download, we can compile just as we did in custom vision, and then we use it in our application. Show that for iOS. So the steps are the same. We download the ML model, we run the compiler, and then we have ML model C. We import that in our application. Now we have to do a little bit more coding to get that working. I created a small service, prediction service, which has two methods. First is we init with the name of the model, and then we classify the stream. So on iOS, this looks a little bit like this. So init is basically, we get the model C, we create an ML model, we create a vision model from iOS, and we're done. So that's the initialization. And then to predict, we get the image stream converted to a UI image. We use vision image request handler to send the image, and we'll create the request. We'll perform on the request handler, we'll perform the request, and then we wait until the classification comes back. So it's no rocket science, but it helps to have the code to base it on. I combined, and I'll share the sources later on, but I combined a number of blog posts and stuff that worked and didn't work to come to this result. So if we run, I can't show this on the video, but laughter and cheers from the crowd will show that it works or not. I think we used this one before, right? So we'll tap on the custom offline train model. I snap a picture, use it. There's still a breakpoint. A number of breakpoints. My code works always from the first. I don't need breakpoints. Alright. And this one says it's 77% dog. So that's good, but it's only 77%, so it's lower than what we have in the custom vision. Now the reason why is probably because in the model that we use to train, this is a very simple model. This is real basic, as was suggested. Use a pre-trained model, and then you'll get much better results. Now for Android, I'll show you. It's basically the same. It's a small script. You need a little bit more info, but so the training stays the same. So you train, you just save it to an H5 file. You specify the file. You get the output names of the model. This is Wi-Fi is going down. I think they're telling us something. So basically, use the script to print the output. So for Android, you need the inputs and the output names of your model. That's something that is generated while you train. So basically, just use a small script, and then you can print those out and pop those into the conversion script. It's a number of steps. I won't go through the entire script, but I think it's 40 lines of Python code to convert it. You write this once and never look at it again. You just convert it. Yeah. This will generate a PB file that you can use in your Android application. So I have a few more slides before we can eat and drink. I think. All right. Okay. So what I recommend, if you want to read, I've written a number of blog posts on fast AI and deep learning AI. Trying to explain everything that happens in the lessons. I have on github.com a number of repositories, but I think the most interesting one is deep learning resources, where there's a lot of, I'll show you. So awesome. No, this is the other one. resources. So there's a lot on benchmarking, blogs, books, build your own deep learning machine, conferences, datasets, frameworks, generative adversarial networks, which we can talk about over beers, research, reinforcement learning, and all links I casually happen to pass by. I started linking some in my presentation, but it was just too much, so you have a look at this one. If you want to dive deeper, I recommend using Fast AI and deep learning in combination. They both have a different approach. Fast AI goes top down. So they say, okay, we have 4 lines of code. It takes you 2 minutes to train a world-class image classifier. And then the further they progress and say, okay, this is a single shot detector that we use to try and train an object detection, and they blow your mind. They show you techniques that, okay, this is some obscure paper that nobody uses, but it works. Why? They explain it, they implement it, it's in the framework, and you can use it. For reference, the guy that wrote the framework and the course, Jeremy Howard, was Kaggle data scientist #1 for 2 years. So Kaggle is an open competition platform for data science. So basically companies post a challenge and then you can submit solutions. This guy was #1 for 2 years, and then he said, okay, let's bundle that up and make a cool little library out of it. Deep learning is from Andrew Ng, professor at Stanford, Google Brain founder, Coursera founder, formerly chief scientist of Baidu, who is now landing AI, deep learning AI. He does a lot and is a walking hero in deep learning. And he starts from the bottom and works his way up. And you look at the videos and he just takes you along for the ride. He says, okay, sure, obviously, yeah, that's sure. And then you have the exercises, and then you go back to the videos. But it's a really good resource. The Fast AI one is free. Deep learning one is like €53 a month. You can finish it in a couple of weeks, depending obviously on how much time you spend working and running and not running. And then obviously a link to custom vision that you can try and play with. I won't publish the presentation, but the idea is to formulate this in a set of blog posts where everything is available that you can just use it to use in your own projects. In conclusion, I hope you have a little bit more of understanding of what deep learning is. If not, please tell me. I would love your feedback on this, as this is the first time I give this presentation. I hope I took a little bit away from the magic that surrounds deep learning, and I hope you can apply it in one of your projects yourself in the future. Thank you very much. Are there any questions at the moment, or do we handle those over drinks and food and I'm up for both. So
if you want to some general question. Are there custom projects out there, customers and companies who request this kind of AI and deep learning stuff?
They don't request deep learning, but I know in Belgium a number of companies that are looking to vision applications. And then you immediately go to deep learning. There's somebody where I won't give too much details that is working on a text classifier to reduce workload of people handling certain files, but I won't dive into too much detail on the record. But I see a lot of vision is a very big market, even so for crops production. They're probably using or looking at something and don't know that it's a problem that can be solved. I'm not talking about autonomous driving. And you can work in different sets of the life cycle. There's a company in Belgium that focuses on labeling data for customers by using people in Mexico Mexico, and I think it's Venezuela. So because labeling of data is still labor intensive. I think they also generate data sets, so using generative models. So based on limited data, they generate new data for training. But I don't have any specifics on that.
I think some years ago, Amazon had a project, Mechanical Turk. So
yes.
Yeah. But for people, just for pointing the eyes or circling some content.
But these guys get paid to link the project to the...
For some cent, mostly. Okay, thanks.
Okay. Let's have some food and beer.
All right.